Hello Year 6 and prospective Wharton Park Year 7 students. I'm very looking forward to welcoming you to Wharton Park in September. My name is Mr. Tipler. I am one of the curriculum leaders for maths here at Wharton Park, and I may be teaching some of you in September as well. What we're going to do today for your transition maths lesson is we're going to look at a bit of ratio and proportion in the real world, and you're going to do a bit of an investigation into find out how golden you are, and to see if you are more golden than your friends and family. So just to get started, what we're going to be looking at first is a bit of sequences. Okay, so just to get your mind in gear, I want you to have a go at finding the rule and the next three terms in each of these sequences. So the first sequence is 1, 4, 7, 10. What's happening each time you go along the sequence? And what will be the next three terms? So I'd like you to pause the video and see if you can find the next three terms and the rule for each one of these sequences. Okay, so hopefully you've paused the video and given this a go. So the first sequence, 1, 4, 7, 10, you might have found that the rule is we're adding 3 each time to give us the next three terms of 13, 16 and 19. Okay, so the rule there was add 3. Question B, we were adding 13 each time, and that gave us 50, 63 and 76 for my next three terms. And then my next three, for question C, we were taking away 6 each time, which then gave me 22, 16 and 10. And then for D, it was a little bit harder because we were introducing decimals and it went into negative numbers, so well done if you got this one. We were taking away 2.5 each time. So the next three terms were 3.5, 1 and minus 1.5. And then E was a tricky one as well because we started in negative numbers but we were adding 2 each time, so then it goes to 0, 2, 4. The questions with the star next to them were a little bit harder. Well done if you got those ones too. So F, we were timesing by 2 and gave us 48, 96 and 192. For G, we were timesing by 10 and we got 2,000, 20,000 and 200,000. For H, we were dividing by 2, so the next three terms were 20, 10 and 5. For I, we were timesing by 3 and we had 81, 243, 729. Well done if you did those ones without a calculator. And for the last one, we were timesing by negative 2, so the signs went from positive to negative, from positive to negative. And our last three terms were 32, negative 64 and 128. So give yourself a big pat on the back if you got all of those right. Well done. Okay, we're going to look at another really special type of sequence. You may have seen it before, you may not have. But what I want you to do, I want you to pause the video in a second and I want you to continue this sequence as far as you can in 3 minutes. Okay, so continue this video as far as you can in 3 minutes. So here's the sequence, 1, 1, 2, 3, 5, 8. Okay, so can you spot the pattern and can you carry on? You've got 3 minutes. Pause the video, give yourself 3 minutes to do so. Okay, well done if you've done that. If you're not sure and you kept on watching, okay, I'll give you a bit of a hint. So the sequence is 1, 1, 2, 3, 5, 8. If we look at 1, 1 and we add them together, we get 2. If we look at 1 and 2 and we add them together, we get 3. If we look at 2 and 3 and add them together, we get 5. Okay, hopefully you can see the pattern now. 3 and 5 makes 8. Okay, 5 and 8 will give me my next term when I add them together is 13. Okay, so if you didn't continue it before, give yourself 3 minutes now, pause the video and see how far you can get. Carry on. Okay, hopefully you found lots of terms. Don't worry if you use the calculator. If you use the calculator, that's fine. Hopefully you found loads and loads of terms in that sequence and kept carrying it on. You may have seen the sequence before. Okay, if you haven't, that's absolutely fine. Okay, this is the sequence we're going to be learning about. But if you have, and you can tell me what it's called, that would be really, really impressive. So if you didn't know, this sequence is called the Fibonacci Sequence. Okay, and it's named after an Italian mathematician who lived in the 12th and 13th century, who called Leonardo Fibonacci. And he discovered the sequence. He was working with some numbers and he invented the sequence of numbers and found some really interesting properties to it. And if we looked at this sequence sort of geometrically by applying some shapes to it, he found that actually if you drew a square, a 1 by 1 square, and then next to it another 1 by 1 square, and then a 2 by 2 square next to that, and then a 3 by 3 square next to that, and a 5 by 5 square next to that, and then an 8 by 8 square next to that. So each square is those numbers in the sequence, the side lengths of those. So we have a 1 by 1 square, and then another 1 by 1 square, and then a 2 by 2 square, and then a 3 by 3 square, and then a 5 by 5 square, which will look like that, and keep doing that around. And this is what this picture here is showing you. Okay, and keep doing that, it forms this pretty spiral. Okay, and this spiral that he discovered hidden in this sequence, he saw that it was hidden in lots of real world places, such as in nature. So you can see a sunflower there, and the seeds of a sunflower have this spiral hidden in there, and the leaves of this succulent plant there, and then even in the shell of an animal, or even in the eye of a hurricane. Okay, all of these things in nature, this spiral can be seen there, and it all comes from just that simple sequence of numbers. Okay, so we're going to look at the sequence of numbers in a little bit more detail, and we're going to find the ratio between each terms. So what do I mean by that? So the ratio between the first two terms is just 1 to 1. Okay, the ratio between the next two terms is 1 to 2. The ratio between the next two terms is 2 to 3, which I could actually simplify by dividing by 2 as 1 to 1.5. So that I want you to do, I want you to write them all as 1 to something. Okay, I'll do a couple more. So the next one is 3 to 5, which is 1 to 1.6 recurring. So if you remember, you might have learned that in school before. With a recurring, we put a dot above the 6. So 1.6 recurring. And then the next one is 5 to 8, which is 1 to 1.6. Okay, so have a go at finding the ratio as far along the sequence as you can. So you carried on that sequence much further than I did, hopefully, and now find the ratio between any two terms. Okay, and what do you start to notice? So again, pause the video if you need to do that, and find the ratio between each consecutive terms in the sequence. Okay, so what you may have found is that if we found, let's take these two for example, the ratio of 89 to 144, so if I do 144 divided by 89 on my calculator, I get 1 to 1.61179775. Okay, so we can see that actually these numbers, they start getting close to 1.61, sorry. Okay, and what that is, the further and further along we go along that sequence, it should get closer to this special number called phi. So it's Greek letter here. So from the Greek alphabet, it's the Greek letter phi, and this number, special number, is 1.618. Okay, and this 1.618 is known as the golden ratio. So when we see this spiral in nature, everything we see in nature with these pictures, we say is in the golden ratio, because we could take this part of the eye of the hurricane and we can times it by 1.6, and we would get the length of this part of the eye of the hurricane. Okay, and we could do that with any consecutive part. Same with here, the distance between this part of the shell and the distance between this part of the shell is in that ratio 1.618. Okay, it's in that golden ratio, and it looks really aesthetically pleasing when we see things in that golden ratio, and that's why artists use the golden ratio in their paintings as well. So we can see two really famous paintings there, including the Mona Lisa by Leonardo da Vinci, and we can see that actually the Mona Lisa's proportion is within the golden ratio. Okay, her length of her head is within the golden ratio of the proportion of her body as well, 1.618. Okay, and even in architecture as well. So in the Eiffel Tower and the pyramids of Giza, we can see that actually this part here, if we measured that and then times it by 1.618, we would get the length from the top of the Eiffel Tower to that middle part as well. Okay, so even in architecture and all these buildings, it's because this golden ratio looks so nice. And even us, we are in proportion to the golden ratio. So we can sort of see this from this diagram here, and if you want to pause it and look at it in a bit more detail, that's fantastic. But we can see that our shoulders to our belly button is in the golden ratio with our belly button to our knees. Okay, we measured our belly button to our knees, okay, and measured our shoulders to our belly button. We would see that that ratio is the same, 1 to 1.618. Okay, if we divided those two measurements together, we should get 1.618, or close to it. So you're going to investigate how golden you are and compare it to other people. So what I'd like you to do is get a piece of paper, if you haven't got one already, okay, and a ruler, and I'd like you to start measuring these things here, okay, and I'll show you a few diagrams of what I mean. If I grab a ruler quickly, I don't have one to hand, okay, but what I'd like to do is get a ruler and measure the top of your head to your chin, okay, or the top of your head to your pupil, and measure each one and label them A. So if you measure the top of your head to your chin, and it might be 34 centimeters, you write down A equals 34. Okay, and if you do them all in centimeters, so top of your head to your pupil, you might get that that's 12 centimeters. I don't know, I'm just making this up, but it could be 12 centimeters. Okay, so measure each one of those. Okay, so if you want to pause the video, measure each one. I'll show you a few diagrams if you're not sure what I mean. So A is the top of your head to your chin, B is the top of your head to your pupil, so your eye level, C is pupil to your nose tip, D is pupil to the edge of your lip, E is the width of the base of your nose, F is the outside distance between your eyes, G is the width of your head at ear level, H is your hairline to your pupil, not your nose, I is your nose tip to your chin, J is your lips to your chin, K is your length of your lips, and L is the nose tip to your lips. Okay, so we can see those here. So A is top of your head to your chin. So if you want to pause this at any time to know which bits you're measuring, so measure each part with a ruler. Try and be as accurate as you can. Try and do it to the nearest millimeter if you can. So top of your head to your chin, top of your head to your pupil, pupil to your nose, pupil to your lips. Okay, then you've got width of your nose, width of your mouth, width of your eyes, and width of your head. And then hairline to your eyes, nose to your chin, and lips to your chin. And then your lips to your nose and the width of your lips. Okay, so measure all of those and label them down. Okay, if you need to pause the video, go back a little bit, that's fine, you can do that. Okay, so what I'd like you to do now is take those measurements, and you can do this for you to begin with, and then you can go back and do it for any person that you want. You can do it for your mum, your dad, your cat, your dog, your brother, your sister. You can do it for a celebrity, you get a picture of a celebrity from a magazine or from the internet. Do it with, I don't know, Harry Kane. You can do it with Taylor Swift, whoever you want, okay? So then what I'd like you to do is take your measurements or the other people's measurements and work out these divisions. So for example, if I was looking at Harry Kane, okay, and I took A, which was the top of his head to his chin, and I divided it by G, which is the top of his nose to, what was G, sorry? G was the width of your head at ear level, so that divided by that, okay, then I might get 1.62. Okay, and if I did B divided by D, I might get 1, for Harry Kane, I might get 1.73. Okay, and then for I divided by J, I might get 1.44. Okay, and there might be something that's different at that. And then what I like to do, if you know how to take the average of all those measurements, so let's say I worked all of those out, took the average, and I got that Harry Kane's average was 1.59. Okay, but then I did it with Taylor Swift, my favourite pop star. Okay, and I did it with Taylor Swift, and I found that her A divided by G was 1.63, and B divided by D was 1.65, and her I divided by J was 1.59. And I worked all of those out and found the average of those, and got that her average was 1.618. Okay, and what that shows is, what we should see is that the closer we are to that number, all these numbers should be close to 1.6. Okay, and the closer we are to that number, the more golden and proportionate we are, so the better looking we are. Okay, so the more proportionate we are and the more golden we are. So if you do this for your for yourself, for any celebrities, your mum, your dad, your brother, your sister, whoever you like, and find that golden. And if you can see that you are in proportion and you come out with your average being 1.618, okay, or as close to the golden ratio as possible, you are really golden, and you can say you're more golden than Taylor Swift or your mum or your dad or whoever. Okay, so a little investigation for you to try. Okay, and you can come in September, and if I'm your teacher or whoever your maths teacher is, you can tell them that you found how golden you were. I hope you enjoyed this video, and I look forward to welcoming you all to Wharton Park in September, and I'll see you all then. Bye.